The biggest mistake that students make when they're trying to find the parts of an ellipse is not writing it in its formal equation. And what I mean by that is setting it equal to 1. So this, we have minus 25. A lot of students will add 25 to the other side, but then they don't get it set equal to 1. And the reason why this is important is because the standard form of an ellipse, or at least one of them, looks like this. All right, notice it's equal to 1. And a lot of students kind of bypass this. They just try to get the x squared and the y squareds, and they get the denominators, and then they kind of totally forget that it's supposed to be equal to 1. It's not supposed to be equal to 25. So a lot of students will add a 25 to both sides, which is absolutely correct, right? Then we have an x squared plus a 25, y squared is equal to a 25. But from this point, we have to be able to set it equal to 1. Because 1, that's also going to give us what our a squared and our b squared is, and then we can be able to identify what is going to be our major vertices, our foci, and our minor vertices. So make sure that you take this extra step, divide it by 25 on both sides. Now what you're going to get here is a x squared over a 25 plus a y squared over a 1. You don't really need to write the 1 there, but I think it's really, really important to make sure for your accounting purposes that you know that there's a denominator there and it's equal to 1. So now we have it in our standard form. You can see here, it's actually the exact replica here. Now remember, there's two different forms of the ellipse. You can have the a squared under the x, or you could have the a squared being under the y. Now, what's the difference between the a squared and the b squared in terms of an ellipse? One thing I want you to hear me, and hear me very carefully, maybe even write it down or just repeat it with me, is that a squared is always larger than b squared for an ellipse. Not hyperbolas, not circles. A squared is always larger than b squared for an ellipse. So how do we know which one's a squared or b squared? It's just the larger one. Since 25 is larger than 1, I know that a squared is equal to a 25, and b squared is going to equal to a 1. These, remember, a represents the distance between my two vertices, or between my two major vertices. B represents the distance between my two co-vertices. And again, this is going to be from the center. Now, since I don't have any h's and k's, right, we're not doing this format, x minus h quantity squared over a squared plus y minus k quantity squared over b squared equals 1. I don't know why I wrote that plus, but that would be if we had our center was going to be off of the origin. We'd have a shift of that center. Therefore, your center would be h comma k. In this case, you can see we don't have that, right? So we know our center is going to be at the origin. And the important thing here is we can say that a is going to equal 5 and b is going to equal 1. If we were going to take the square root, you could do the plus or minus because you are going in the positive as well as the negative direction. But I think it's really important to recognize here is the correct form. Now, I probably thinking, knowing what this problem was going to be, I wrote in this form, right? But again, our a could either be under the x squared or our a could be under the y squared. Those are going to be your two different forms. So it's really important when trying to identify your parts of an ellipse, mainly the vertices as well as mainly the vertices, is to understand, is this a horizontally stretched ellipse or is this a vertically stretched ellipse? Well, when your a squared is under your x, that means your major vertices or your major axis is going to be horizontal. When your a squared is under a y, that means you're going to have a vertical one. So let's just try to get a nice little idea or vision of this ellipse. So we have a center. A equals 5. That means the distance from my major vertices from my center is going to be 5 units. Now that's going to be to the left as well as to the right, because again, think about it. If you were to take the square root of a squared or square root of 25, you're actually going to have a plus or minus, right? You're going in that positive and negative direction. Since my a squared is under x, that means that distance is going to be a horizontal 5 units. So 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. Those are going to be what we call our major vertices. Now, there are a couple different ways we could go ahead and write that. You can, a lot of times I just allowed this for my students to do plus or minus 5 comma 0, or you could actually write out 5 comma 0 and negative 0. And then we have b, which is going to be the distance from our center to our co-vertices. And again, that's just going to be in the opposite direction. So if my major vertices are horizontal, that means my co-vertices are going to be vertical. And for these, I'll do co-vertice and a co-vertice. So again, we can just do that, but now we're going to be changing them from the y values. All right, and then last but not least is going to be the foci. So the foci is going to be all about our relationship between our a and our b. And there's a little bit of a formula that we need to be able to apply. So the understanding what our c is going to be c squared is going to equal to an a squared minus a b squared. So that's all we simply need to do, understand the relationship. Now this relationship is unique for an ellipse. It's going to be different for a hyperbola. So just like I said, a squared is always larger than b squared for an ellipse, always remember that a squared minus b squared is going to give you c squared for an ellipse. So now we just know that c squared is going to be the square root, or if we were to subtract those in our case, so we'd have a c squared is going to equal a 24. And then you could simply go ahead and, simplify that square root if you really wanted to. And actually I'm going to, because I want to get kind of like a decimal equivalent of where exactly we're going to be at. So therefore I could say c is going to equal the square root of 24. And I'm not really sure what the square root of 24 is. Actually, you know what? I'm not going to simplify this. I have another way to approximate it. What is the closest number that I can take the square root to 4 on? Well, I know that 25, the square root of 25 is 5, and the square root of 16 is going to be 4, right? So I know that the square root of 24 is going to be some number or some decimal between 4 and 5. And it's going to be really, really close to 5, right? So therefore, I can just say it's going to be 4 and change, but really, really close to 5. So let's just do that. 1, 2, 3, 4. And let's just, I don't really have much room over here, but we'll put it right there. And then you can just kind of see that's like that. And again, the reason why I went to the left and to the right is because the foci and the major vertices all lie on the major axis. So that's why I wanted to move those. Now, again, if you wanted to simplify this, you know that 6 times 4 is 24. So therefore, you could rewrite that as a 4 times 6. And then you know that the square root of 4 is going to be 2. So therefore, that'd be 2 square root of 6. Voila, there you go, ladies and gentlemen. We have identified all the major parts of an ellipse and avoided our common mistake.